Hello. So in this final video, we're going to look at the last question of the review packet, which has to do with equilibrium. Specifically, this question 40 has to do with Le Chatelier's principle. Okay, so Le Chatelier's principle was essentially the idea that if there is a system at equilibrium and a stressor is applied to it, so some sort of change, the system is going to do whatever it can to account for that change and basically counterbalance it. So if you make more of a product, or excuse me, if you add more of a product, the system's going to balance that out by trying to take away some of that product. If the temperature increases, the system's going to try to balance it by doing something that would decrease temperature, and so forth. So we're going to look at these 6 different stressors and see, first off, if they even have an effect on the equilibrium of this particular system and reaction, or if there is a change, what that change would be. Okay, so let's dive into these. I'm actually not going to do them in order. I'm going to go in order of what I think are maybe some of the easier ones moving on, but let's take a look at these. So we're looking at our reaction right here. Okay, so we're going to start with C, actually. Okay, so part C says what would happen if hydrogen was removed. Now, if we look at where hydrogen is in our reaction right here, it is a gas, so it's definitely part of our equilibrium expression. Remember, solids and liquids are not part of the equilibrium expression, but gases and aqueous solutions are. So it's definitely part of the equilibrium, so removing some hydrogen is definitely going to have an effect, and it's a product right now. So if we are removing hydrogen, that means that we now have less hydrogen in our system. So to counterbalance it, the system is going to make more hydrogen. So how are we going to make more hydrogen? The only way for that to happen is if our reaction shifts towards hydrogen, because that would be towards the production of more hydrogen. So that means that if we removed hydrogen, the system would shift, oops, wrong one there. The system would shift to the right, which means that this would favor the forward reaction until the system gets back to equilibrium. Okay, so that would be for part C. Okay, so now we're going to move on to B. So remember I said we're going out of order here. So if we go to B, let's look where this is in our reaction. So it says that for part B, we're adding magnesium to the system. Now, normally the system would, if you're adding something, try to remove it to counterbalance that. But this is a little bit of a trick question, because if you look at magnesium in our reaction here, notice that it is a solid. And as I mentioned earlier, solids and pure liquids are not included in the equilibrium expression. So even though we are adding more of something, since it's not in our equilibrium expression, this would actually have no effect on our system. Had magnesium been a gas or an aqueous solution, then adding it would have forced the reaction to the right, but since it's a solid, it actually has no effect. So those were our 2 examples that we're dealing with the addition or subtraction of a reactant or product. So let's look at another one. So let's go up to part A. So part A deals with temperature. Now, when you're dealing with temperature in Le Chatelier's principal questions, what you want to think of is, first off, if this reaction is exothermic or endothermic, and based on that, where heat would show up in the reaction. So would it be more of a product or more of a reactant? So because our delta H is negative, that means we have an exothermic reaction. And since it's exothermic, that means heat is being produced or given off. So what I'm going to do is I'm going to actually write heat over here as if it were another product. Okay, so now we're going to look at this the same way we looked at B and C, essentially. Okay, so if we're increasing the temperature, the system wants to do something that would decrease the temperature. So if the reaction going to the right makes more and more heat, that would definitely increase the temperature. But if the reaction shifts to the left, that's going to be moving away from the heat, which would indeed decrease the temperature. So because heat is over here as a product, if we want to decrease the temperature, we're going to actually shift towards the left in order to counterbalance that. So we'll say shift left, or you could say favors reverse reaction. Okay, so that's what you do with temperature. Think of, is it exothermic or endothermic, and is heat then a product or a reactant? Okay, so now let's move on to part D. So part D says, what would happen if you add a catalyst? Now again, it seems like a little bit of a trick question. If you're adding a catalyst, catalysts affect rates of reactions, but they actually have no effect on the equilibrium. So we can say changes rate, just so we know that it does make a difference, but not necessarily for what it's asking about. So changes rate, but no effect on equilibrium. There we go. Sorry, getting a little scrunched at the end there. Okay, so there we have that one. Now let's look at E and F. E and F we can sort of look at together because both of these are dealing with pressure and volume. And what we know from Boyle's law, thinking back to our gas laws, remember Boyle's law was this formula, that pressure and volume are inversely related. Meaning, if one goes up, the other goes down. Okay, so depending on how you think about this, you could either think of both of these in terms of pressure or both of them in terms of volume, whichever one makes more sense to you. Okay, so let's look at these. So if we start with E, E says we're decreasing the volume of the container. So if you would rather think about this in terms of pressure, you can. So I'm just going to write a note to myself underneath that decreasing the volume would increase the pressure. Okay, so let's think about it this way. Our system now has less space for these particles to occupy, and the ones that we're really concerned with if we're talking about pressure and volume are the gases. So let's look up at our reaction at the top. We only have one thing that was a gas, which was over here. Okay, so I have 1 mole of gas on the product side and 0 moles of gas on the reactant side. So if our volume has gone down and the pressure has gone up, the system wants to counterbalance that by doing something that would actually create less gas, because that would mean fewer collisions and therefore lower pressure, and less gas would, be more happy in a smaller volume than a larger amount of gas would be. Okay, so I like to think of it in terms of pressure, but again, it's up to you which one you prefer better. So since we decided that a decrease in volume means the pressure was going up, we definitely don't want to continue to make more gas because that's just going to keep increasing the pressure, and we already have done that. Remember, we're trying to counterbalance this. So rather than making more gas, our system's actually going to shift to the left because that would then decrease the pressure and counterbalance what we're seeing here. Okay? So we'll say that for part E, this would shift to the left and favor the reverse reaction again. Okay. For our final question, if we take a look at F, F says decrease the pressure. So again, if you'd rather think of it as increasing the volume, that is fine. But if the pressure has decreased, we are trying to, or not we, but the system will do something that would increase the pressure to counterbalance that change. So to increase the pressure, you want more collisions between the gas particles and the walls. So the only way to get more collisions is to have more gas added to our system. So this time, since the pressure decreased, the system's going to adjust towards an increase in pressure, meaning more gas produced, so it will shift towards the right. So for our final one, we'll say that decreasing the pressure would, let me do this on the bottom here, would shift to the right, and in other words, favor the forward reaction. Okay, so there's just a few examples with Le Chatelier's principle. Your options will always be shift right, shift left, or no effect. And it all depends on what the original change was. The system is going to do whatever it can to try to counterbalance whatever that change is. Okay, so think what happened, and then think how can I make the opposite happen by either going forwards or backwards. So that's the basics of Le Chatelier's principle.